Welcome to Intel Agilex 5 FPGA GTS Transceiver Basics online training. My name is Neil. The Intel FPGA portfolio supports this transformation, including discrete and integrated FPGAs that are expected to improve processing efficiency, task specificity, and connectivity. Intel FPGAs can provide a variety of workloads in network processing, as well as compute and storage acceleration. FPGAs are mass-produced, standard product ICAs that can be reconfigured in the field to accelerate virtually any digital algorithm. They offer greater throughput, execution speed, and energy efficiency than CPUs on computationally intensive parts of algorithms, but with the ability to adapt quickly to changes in algorithms, data patterns, or performance needs. They can be reconfigured in the field to accelerate virtually any digital algorithm. They are available in 5 current families: Max, Cyclone, Aria, Stratix, and the newest family Agilex, all with of increasing capacity, performance, and feature sets. In this training, we will cover 3 main topics. First, GTS Transceiver Architecture Overview. Second, GTS Transceiver Channel Placement Rules, followed by GTS Transceiver Architecture Comparison against prior Intel FPGA families. Let's start with GTS Transceiver Architecture Overview. A transceiver is a combination transmitter and receiver used by applications to provide high-speed communication. Term high-speed could mean hundreds of megabits per second to the hundreds of gigabits per second range, depending on the requirement. A transceiver allows this communication to use a variety of different physical mediums depending on the application. It could be simply across a board or a backplane, or across an optical fiber or cable of some kind. Thus, they are used in the physical layer of the Open Systems Interconnection OSI model, the model used to describe the functionality found in the interconnect protocols of most communications, networking, and computing systems. As part of the physical layer, they serve as the interface between the digital realm and the analog transmission domain. Depending upon your physical medium and the high-speed protocol in which you want to support, you may require specific features from your transceiver. Some application-specific standard products, or ASSPs, since they are designed to support select applications or protocols, will implement only certain features of the transceiver. Since FPGAs are designed to be generic and support a wider range of protocols, their transceivers are much more configurable. The transceiver makes up 2 sublayers of the physical layer, namely the physical coding sublayer PCS and the physical medium attachment PMA. The role of the transmitter path is to convert parallel data patterns into serial data that can be transmitted at high data rates. The transmitter must also embed the sampling clock into the serial stream. Thus, the clock can be extracted at the receiver and then be used to sample the incoming data. To embed the clock, the transmitter needs to ensure that there are adequate number of transitions in the serial data string for a receiver phase lock loop to be able to detect the appropriate clock rate and lock onto it. The transmitter may also reformat the data to correct for potential errors that may arise due to signal attenuation and data corruption from the transmission medium. The receiver must first extract the clock from the incoming data. It then uses that clock to sample the incoming data stream. Next, it converts the serial data into parallel data and locates the incoming byte boundaries to which it aligns itself. Finally, it must undo any transformations performed on the data by transmitter to restore the data back to its original form for presenting to the FPGA logic, checking to make sure data has not been lost in the process. The receiver path has more work to do than the transmitter path. Thus, it contains more blocks and more complex blocks than the transmitter path. The transmitter and receiver implement the PMA and PCS layers of the PHY. The purpose of the PMA is to convert the data in between the parallel digital domain and the serial analog domain. The PMA could also connect directly to your physical communication medium, like a board trace, or it could connect to another device that connects to the actual physical medium, like an optical transducer, converting the electrical signal to and from light. Examples of PMA functions include parallel to serial conversion and the inverse serial to parallel conversion. The PCS is the digital portion of the physical layer. In the transmitter, its job is to prepare the parallel data for transmission across the physical medium in a way that the data can be recovered at receiving device. Examples of transmitter functions would be encoding or scrambling. In the receiver, the job of the PCS is to return the transmitted data back to its original form. Receiver tasks would include locating the original byte or word boundaries of the incoming data, as well as decoding or descrambling the data stream back to its original form. Connected to these layers inside the device are one of several blocks. Sometimes it is simply data generation and capturing logic, with control of transceivers provided by a processor or state machine logic. For more complex protocol implementations, you find a Media Access Control or MAC block. The MAC is responsible for managing the transactions through the PHY. It receives data or information from the upper layers and assembles the packets to be given to the PCS for transmission across the link. It disassembles any packets received from over the link. Any errors or faults generated during transmission from the link are decoded and handled by the MAC in order to maintain communication between the endpoints. In a sense, the exact data content the MAC transmits or receives is not important, just as long as the link continues to function correctly. The layers beyond the MAC, then, are more concerned with where the data is actually going and what data is being sent and received. The Intel Agilex 5 FPGAs and SoCs are equipped with non-return to 0 NRZ GTS transceivers optimized for a wide variety of applications, ranging from 1 gigabits per second to 28.1 gigabits per second NRZ. The monolithic GTS transceivers in Intel Agilex 5 FPGAs and SoCs enable low latencies for edge or mid-range FPGA applications. For long-reach backplane driving applications, the devices use advanced adaptive equalization circuits to equalize system loss. Welcome to Intel Agilex 5 FPGA GTS Transceiver Basics online training. My name is Neil. Intel Agilex 5 FPGA GTS transceiver channels are equipped with the following blocks. Dedicated PMA provides primary interfacing capabilities to physical channels. Hardened PCS supports 64-bit, 66 bits encoding and decoding, data scrambling, block alignment, and gearboxing functions. FEC Firecode FEC for 10 and 25 GBE base CKR/CR applications, and Reed-Solomon FEC. Ethernet Hard IP up to 610G 25G MAC. A single TMA PCS channel with independent clock domains forms each GTS transceiver channel. Using a highly configurable clock distribution network, you can configure various bonded and non-bonded data rate within each GTS transceiver bank. GTS transceiver is monolithically integrated to core fabric for greater efficiency in lower power consumption and smaller form factor. The GTS transceivers have an NRZ serial interface with an advanced PMA and multiple hard IPs. This allows efficient implementation of popular and emerging serial protocols. GTS transceiver has E and D series. The table here shows the high-level differences between E and D series transceivers. The difference is in performance and resources. E-Series is the baseline which contains device group A and B in it. B group is the baseline with lower data rate of 17.16 gigabits per second. Device group A has a higher max data rate of 28.1 gigabits per second. Device group B has PCI Express HIP that is running in 3.0 and 4.0 for certain devices. It has Ethernet running at 10G and forward error correction FEC supporting 10G data rate. Compared to Group B, the Group A has PCI Express HIP running 4.0 and Ethernet HIP running at 25G, so the FEC is also supporting 25G data rate. In D series, there are more PMAs available, The max data rate is 28.1 gigabits per second. PCIe HIP is scaled to 4.0 by 8, up to 1625G max. Lastly, the USB 3.1 HIP runs at 5G speed. The HIP controller resides in an HPS block, but it uses transceiver resources to achieve 5G speed. Transceiver Bank is the main building block of the transceiver. It is comprised of 4 PMAs, hard IPs such as FEC, PCS, Ethernet MAC, and PCIe. It also has one system PLL and reference clock network that support both system PLL as well as PMA. All of these resources are contained in a bank itself. The reference clock spans across multiple banks. The number of GTS transceiver banks varies depending on device density and package variants. In the next few slides, we will go over how the collections of these banks form the layout of the actual Intel Agilex 5 devices. Let's look at the GTS Transceiver Bank B32A Layout. We start with the E series shown on the left side. This is a 5096 pins ball layout. There is one bank A, and the number in red here denotes the total number of GTS transceiver channel count. The numbers 008 and 013 are basically referring to the density type. As you can see, the bigger device's density 028 has 3 banks, one on the right side and 2 on the left side. Even bigger density 043 has 2 banks on the right and 2 banks on the left side. Continuing to the largest densities 052 and 065, you get 3 banks on either side. The way how we scale these is by referring to migration. Banks in each horizontal line can migrate, and then we add more banks in next horizontal line as we move to larger densities. HPS is located here right on top left adjacent banks. This is important as later in the channel placement, HPS dictates how the USB design is supported. On the right side, we see D series, where it starts with 16 GTS transceiver channels with 2 banks on each side. The largest density has 4 banks on each side. HPS is in the same location on top left, just like in E series. This slide shows the GTS Transceiver Bank in B32A package, which is 8820 pins of ball anywhere package. This package is available in both E and D series as shown here. The banks that are marked with stripes basically show banks that are down bonded. Down bonded here refers to the pins that are not bonded out for the channels and the reference clock. As a result, we lose the transceiver channels in these particular banks. The reason why it's still shown in the diagram is because in the Intel Agilex 5 devices, for the down bonded bank, even though the transceiver resources are not available, you will still have the system PLL. One system, PLL, exists in the bank which is available for core fabric use. For this particular package, the maximum number of GTS transceiver channel count is 12. In the D series as shown, the rightmost banks on the right side of the device are down bonded. The last smaller package is M16A, which is shown here. M16A is an 896 pins of standard ball grid array align layout. This is just for E-series device Group B and gives you maximum of 8 total channel count. Here is a quick overview of the GTS Transceiver Bank building blocks. The PMA is basically NRZ, and you have individual TX, PLL, and CDR for independent channel operations. FEC supports the Fire code as well as RS for the 25 gig. PCS does not support 8 bits, 10 bits, but only supports 64 bits, 66 bits data scrambling, block alignment, and gearboxing. Ethernet MAC supports 10G 25G with 1588 PTP and ANLT. PCI Express HIP supports 3.04.0 and by 4 and by 8 configurations. For the clock side, as usual, we have the reference clock network that supports the reference clock for the TX PLL, CER, system PLL, and the data path. Basically, it helps to provide the clocks for the PMA and the hardened IPs in passing over the data to the core. Bonding configuration is also supported, and on top of it, we have the dedicated CDR clock output. It is used if you need to route the recovered clock from the CDR directly to a bit. The access to the Configuration Shift Register CSR and dynamic reconfiguration of transceiver channel is supported via the Avalon Memory Mapped interface. This slide shows GTS Transceiver supported configurations overview. The view here is in terms of the resources that you can use for different configurations. In all configurations, the PMA will be used because that is the basis of transceiver. In the case of PCIe controller, PCIe hard IP and PMA are used. With Ethernet controller, you have choice whether FEC is used or not. For hardened USB 3.1 controller, you are only using the PMA resource in the transceiver, and the actual controller resides in the HBS. Similarly, for PCS, FEC, and PMA Direct, the corresponding resources have been checked in this table. Next, we will look into GTS transceiver channel placement rules. Here is a channel placement rules summary. The channels in the PMA connects to each of the hard IPs such as PCIe HIP, PCS, FEC, MAC, and USB. For MAC and USB, it depends on whether that particular PMA has the access to those resources in terms of availability, or it can go through the core fabric directly. In the next two slides, we will see where the channels actually can be placed. Rule number 1 is about hard IPs. As I mentioned earlier, the hard IPs have fixed locations. The hard IP here refers to the PCIe, Ethernet, and USB. PCIe has a dedicated location that allows by 1, by 2, by 4, and by 8 configuration. The Ethernet with MAC has dedicated 1 or 2 channels per bank, 1 for the E-series device family and 2 per 2 channels per bank in the D-series. USB is only available in 1 channel per device, and you can implement it on a specific location that allows only 1 channel in the whole device. Rule number 2 is about bonded mode. When you implement a bonded PMA, FEC, or PCS Direct, then that is in a fixed location, where you can implement the bonded according to the by 2, by 4, by 6, or by 8 modes. Rule number 3 is about non-bonded mode. In non-bonded case, PMA, FEC, and PCS Direct can be in any location. How do you look at these hard IP locations? Basically, the PMA resource ties to the configurations shown on the right of it in this diagram. We'll start with PCIe hard IP as shown here. In the PCIe hard IP section, on the left there is the PMA. On the right side, you can see the configurations that are being supported. For by 1, by 2, or by 4, you have to implement it in the specific location as shown here. Basically, by 1 on channel 0, by 2 on 0 and 1, and by 4 on the same bank. You cannot straddle as it cannot support any other locations than the ones shown here. For my 2 across the 2 banks shown in light green, the specific sequence supported is A and B and C and D. For the E-series, which has only 3 banks, we only have A, B, and C banks. By 8 is not supported in the E-series, but only in D-series. Channels that are not used by PCI candidate can implement other configurations as long as they are valid configurations. For example, on the Ethernet side for the E-series, there's only 1 Ethernet MAC, and it's at channel 3 as shown. For D-series, there are 2 on channel 2 and 3 as shown. USB 3.1 is only available on the transceiver bank directly adjacent to the HBS block. As shown earlier, the HBS block is on the top left corner, so only those banks directly adjacent to that HBS supports the USB. It is only available in channel 1 or 2 as shown, so you can pick either one of those 2 channels to connect to the USB 3.1 controller in HPS. For the bonded case, these are the only supported locations. By 2 must be 0, 1, or 2, 3, as shown in light yellow color. By 4 must be within the same bank, as shown in orange color. By 6 must be starting from the lower bank on channel 2 all the way up to the adjacent bank for the full bank support. By 8 must be fully occupying 2 banks. One thing to note here is that the FEC Direct only supports by 4 bonding that is used to implement 4 by 10G Firecode mode. Let's look at the use scenario rules. The primary use scenario is related to the architectural design where the same system PLL is used when you configure in certain modes. For example, in the FEC case when you have multiple interfaces that use the FEC in the same transceiver bank, then all the FEC interfaces must use the same system PLL. For the dual simplex case, where you implement independent simplex TX and a simplex RX placed in the same GTS transceiver channel, if you selected a system PLL to clock both of them, then you have to use the same system PLL to do that. For bonding, when you bond the channels using a system PLL, they must all use the same system PLL. On top of that, for those simplex cases, you must also use the same segment if you enable the FEC for both the TX and RX. There is only one AVMM access to the channel. If you have 2 different TX simplex or RX simplex, then you either must share one interface or enable an arbiter logic if you need independent access to the both TX and RX. As of now, the arbiter logic is available as a choice in the IP when you need to enable the different interface to those simplex. If your design has a GTS transceiver, then you must provide an external clock to OSC_CLK_1 pin. Here, we will talk about how to address the unused PMA. Intel Agilex 5 device has an ability to support power down. Let's start with E-series first. Power down basically means grounding a particular bank. If you permanently do not need to use the channels in the bank, then whole bank can be grounded. In order to do that, you can connect the PMA power rail, which is the VCCEHT_GTS and the VCCERT_GTS to the ground. There are 2 conditions. In condition 1, entire right side or left side can be powered down. This includes all banks on that side. In condition 2, only specific 1 or 2 banks that support power down to ground. In this diagram, green oval shape is used to indicate which banks can be powered down. As you can see, bank A or B can be powered down. Architecturally, you cannot jump the banks, so you start power down from the lowest bank, and you can't arbitrarily power down bank A and C, for example. Certain devices don't support power down at all. The power down support for the D series is similar to what we saw in previous slide for E series. You can power down specific 1, 2, or 4 banks that support power down to ground. For larger densities 051 and 064, power down is done in a group of 2. If you don't need some banks, you must power down both A and B together. For the 3 smaller densities 010, 025, and 031, the power down can be supported at 1 bank basis, which is applicable for both packages, B32A and B23A. If there is unused PMA that is currently not in use, but you plan to use it in the future, then you have to preserve it. In the first scenario, if you have the whole unused bank, then you cannot power down the bank and must keep the PMA power supplies connected to GTS Transceiver Bank. In the second scenario, where you have unused PMA channels that you don't need to use, but you need to use them in the future, and it is not currently in your design, then no action is required. The device has a way to preserve it without any user intervention. In the third scenario, if you have unused PMA channels that are instantiated in your design and fully connected, then for future usage, you need to hold TX and RX PMA in reset by asserting the I_TX_reset and I_RX_reset ports of the GTS PMA, FEC, Direct PHY, Intel FPGA IP. The other requirement here is for those PMA channels that you have it in operations. You have to make sure that the data patterns are actually toggling and not sending all zeros or all ones. You also have to hold the TX and RX PMA channels in reset before disconnecting the reference clock. Let's examine the GTS transceiver architecture comparison against prior Intel FPGA families. The biggest difference, as compared to prior families, is the RSFEC that works for 25 gig. GTS does not support 8B, 10B in PCS as well as in Interlic and PCS. That capability needs to come from soft IP instead. In GTS, you get all the way up to PCI 4.0, 25 gig eHIP per bank, and USB 3.1. PMA hard IP mapping is about the same in GTS. Here are some more differences. Main points about GTS transceiver are independent TX PLO per channel and GTS, system PLO per bank, and additional option of RIF clock coming from HVIO. In summary, Intel Agilex 5 family delivers monolithic integrated GTS transceivers with cost and power optimized solution. It is built upon F-tile architecture with flexible configurations of PMA and offerings of hard IPs targeting PCIe 4.0 and 25G Ethernet that simplify and accelerate high-speed interface design planning and implementation. Detailed info can be found in Intel Agilex 5 Family GTS Transceiver User Guide. Thank you for attending this training.